All right, let's get right into it. We're going to talk about something fascinating and honestly super important that's happening right where AI and medicine meet. It's a story about teaching a machine to see, a hidden flaw that could have major consequences, and a really clever fix that changes how we should think about building AI. So here's the big question, right? Can we actually teach an algorithm to look at a medical scan, like an X-ray, and find signs of disease as well as a human expert? Maybe even better? This is one of the huge promises of AI in healthcare today. And you have to understand the scale we're talking about here. It's massive. Globally, we take about 2 billion chest X-rays every single year. It's one of the most common medical tests on the planet. So if we can get this right, it could literally help millions of people by catching diseases like cancer or pneumonia way faster and more accurately. The stakes are incredibly high. So how in the world do you teach a piece of software to see something as complicated as a tiny mass on a lung X-ray? Well, it all boils down to a process we call training. It's actually pretty straightforward, at least on the surface. You can think of it in 3 basic steps. First, you feed an X-ray image into the system. Second, the AI algorithm, this complex neural network, goes to work analyzing all the pixels and patterns. And third, it spits out what's called a probability score. It's just the AI's best guess, saying, I think there's a 70% chance this is a mass, or whatever. Now, you gotta remember, when the training first starts, the AI is completely clueless. I mean, its guesses are basically random. So for an X-ray that we know has a mass, where the correct answer, or label, is 1, the AI might guess a probability of 0.48. And for a normal X-ray labeled 0, it might guess 0.51. It's basically just flipping a coin. The whole goal of training is to get those guesses way, way closer to the correct answer. Okay, so how does it actually get smarter? Well, this is the crucial part. The AI learns by figuring out how wrong it is. You can think of it like a game, where the whole point is to get your error score as low as you possibly can. And the way we measure that error is with something called a loss function. The easiest way to think about it is like a golf score. A perfect prediction gets a score of 0, but a really bad guess, that gets a really high score, a huge penalty. So the AI's entire job during training is to tweak its own internal logic over and over to get that total loss score as close to 0 as possible. And we're not talking about a few dozen pictures here. This algorithm is shown hundreds of thousands, sometimes millions of these labeled X-rays. For every single one, it makes a guess, it calculates its loss, its penalty score, and then it makes a tiny little adjustment to try and do better next time. It does this over and over and over again, slowly getting better at telling a healthy lung apart from a sick one. Okay, but here's the twist. This is where this whole idea of learning can go seriously, dangerously wrong. What happens when the data we're using to teach the AI is, well, lopsided? This is a reflection of reality, right? In medicine, most people who get an X-ray are actually healthy. So in any real-world data set you collect, you might have, say, 99 normal X-rays for every one single X-ray that shows a mass. This is a huge problem in AI called class imbalance, and it can cause the learning process to go completely off the rails. And here's the scary consequence. Because the AI is seeing an overwhelming number of normal examples, it learns a dangerous shortcut. It figures out, hey, if I just guess normal almost all the time, my overall error score will be pretty low. It gets lazy. It starts to ignore those rare but incredibly important disease cases because, frankly, they don't affect its overall score that much. Let's walk through a little example to see exactly why this happens. Imagine we have a tiny data set of 8 patients. 6 of them are normal, and 2 of them have a mass. At the start, the AI is just guessing 50-50 for everyone. Because its guess is so non-committal, the loss function gives every single patient, healthy or sick, the exact same penalty score. Let's just say it's 0.3. And this is where the bias really kicks in. Look at the math. The total penalty, or loss, from the 6 normal patients adds up to 1.8, but the total loss from the 2 patients with a mass is only 0.6. So, if you're the AI and you want to lower your total score as fast as possible, what do? You focus all your energy on getting the normal patients right, because that's where the biggest penalty is coming from. The 2 sick patients? They pretty much get ignored. So this sounds like a disaster, right? A biased AI that ignores sick people. But thankfully, there's a really elegant solution to this. And we don't need to go out and find more rare data. We just have to change the rules of the learning game itself. The fix is called a weighted loss. It's a simple but brilliant idea.
We basically tell the AI that making a mistake on one of the rare cases, the patients with a mass, is way more costly. We tweak that loss function so that it applies a much higher penalty for any errors it makes on that small but critical group. Let's go back to our 8 patients, but this time we're going to apply these weights. Since there are way more normal patients, we give them a low weight. And since there are only 2 patients with a mass, we give them a high weight. This basically magnifies the penalty for any mistakes made on the sick patients while shrinking the penalty for mistakes on the healthy ones. And here it is. This is the aha moment. Look at that. The total weighted penalty from the normal patients is now 0.45, and the total weighted penalty from the patients with a mass is also 0.45. The scales are perfectly balanced. Now the AI has an equal incentive to get both groups right. It can't get away with ignoring the rare disease anymore. It is forced to learn how to find it. So, what's the big takeaway from all this? First, real-world data is messy. It's almost never perfectly balanced. Second, if we're not careful, that imbalance can create really dangerous biases in our AI models, teaching them to ignore the very things we need them to find. But, and this is the most important part, we can fix it. By changing the AI scoring system, we can rebalance the scales and force it to pay attention to those rare, critical events. And this isn't just about X-rays. This is about fraud detection, finding manufacturing defects, you name it. And that leaves us with one last really big question. This problem, class imbalance, is just one type of bias that can creep into our algorithms. So as we start to rely on AI for more and more important decisions, we have to constantly be asking ourselves, what other hidden biases are we teaching our machines, and how do we find them before they cause real harm?